everyone. Seeing as we're not going to be able to be in class tomorrow, Wednesday, we are going to go ahead and cover a couple of topics using video so that we don't fall behind for the rest of the term. And so what I'd like to talk to you about today is this idea of isomerism. So where we left off last time, we were talking about isomers were compounds that have the same molecular formula, but they still differ in some way. The easiest type of isomer that we can wrap our heads around is this idea of a structural isomer. Things that have the same molecular formula, but our atoms are connected in a different order. So for example, structural isomers could be this cyclic ether here versus acetone, which is this ketone. They have the exact same molecular formula, but where they differ is in the way that we've connected our atoms together. A second type of isomer we've talked about is this idea of a cis-trans isomer, or a geometric isomer. A geometric isomer is a type of isomer that differs in that it has the same molecular formula, but it differs across a rigid plane. The example we gave you at the end of class on last Friday, I guess it was, yikes, was this idea of butene. 2-butene can either look like this or like this. And we talked about the fact that unlike a single bond, double bonds can't rotate around that bond. Meaning that if two groups, in this case methyl groups, are stuck on the same side of the double bond, they're not going anywhere. They are absolutely stuck there. On the same token, if these two groups are on opposite sides of the double bond, they're stuck there as well. The connectivity for these two molecules is the same, in so much as their name is exactly the same from what we've talked about so far. So this is called 2-butene. Whereas this molecule over here is also 2-butene. We mentioned earlier that when talking about isomerism, we need to be very careful about coming up with a set of names that allow molecules to be differentiated from each other. So every unique molecule will have a very specific unique name. And so we need to add a descriptor to these two molecules that differentiate them as what we call geometric isomers. They differ across a rigid plane, and the rigid plane in this case is our double bond. You can't rotate around it, it's rigid. And so what we'll do is we say that when two groups are stuck on the opposite sides, we're going to call them a trans isomer. And trans in this case simply means different. On the other hand, if two groups are stuck on the same side of the double bond, or a rigid plane here, we're going to call this a cis isomer. And cis in this case simply means the same. And so what we're going to learn over the course of the next video or two is a way in which we can tell molecules are either cis double bonds or trans double bonds. And so with something that only two groups are attached to each of the double bonds, there's two methyl groups, they can either be on opposite sides or on the same side, this winds up being relatively straightforward. Where this becomes a little bit more challenging is when we have more than one group attached to both sides of our double bond. So for example, we have a group that looks like this, where we've got a fluorine attached to the double bond, we've got a methyl group attached to the double bond, a hydrogen, and a methyl ether group. It's a little less clear which groups are on the same side or which groups are not on the same side because we're not sure what winds up being the most important. And so where we're going to go in the next video is how to determine A, which groups take what we call priority when looking at a double bond, and how to go ahead and say that, okay, this double bond can be described as cis or trans. So stay tuned, guys.